This is a review of partial differential equations, but first we will go through the finite difference methods. The topic is introduced in 27.12 for the ordinary differential equations. Main idea is to replace the derivatives with the finite difference divided differences as shown in figure 23.3 of Numerical Methods by Chapra. This replacement turns the differential equations into a set of algebraic equations, and these algebraic equations are easily can be used to solve the ordinary differential equation and the partial differential equations. For example, the ordinary differential equations boundary value problems are solved in chapter 27. For example, you can see 27.3 on page 784, while partial differential equations are being solved with the method of finite difference method in chapter 29 for the elliptic equations, and in chapter 30 for the parabolic differential equations. So for the ordinary differential equations, ODEs, the finite divided difference method is used, and the example taken is it's a rod with temperature T1, the first temperature, and the other temperature at T2. TA is the environmental temperature, and the distance we are going to take is let's say it is the distance step is delta x. So we start from one point, then we move to the other point, then the next point after delta x, and we use subscript I to highlight the movement. This is I. So the temperature here is Ti. The previous temperature at the node will be Ti minus 1, the next will be Ti plus 1, and so on. And keep in mind that I is a relative sort of operator that will move. So for the next node, we see there is a shift between Ti minus 1, Ti plus 1, so this becomes Ti, and for the third time the Ti is shifted here, and so on. So example of the steady state equation for temperature of the rod, we have the second derivative of temperature, h bar Ta minus T. H bar is a constant, Ta is the temperature of the surrounding air. Based on the finite divided difference approach, the second order differential can be represented by the centered divided difference formula: Ti plus 1 minus 2 Ti plus Ti minus 1 divided by delta x square. This is we will substitute this value back here, and this equation will be, the equation 1 will become like this. It's going to be further rearrangement, and this will become algebraic equation. Now here we have the variables Ti minus 1, the Ti plus 1. Note down that for the first time this value is the left side on the rod, which is the temperature is given. This is unknown. This is first interior node, this is the second interior node, and the value on the right side are known, given. So we will directly switch to example 27.3, where a rod of 10 meters is given with the constants h bar. Ta is given 20, delta x is 2 meters, and the initial conditions or boundary value conditions are given: T0 equals to 40 and T10 equals to 200 degrees centigrade. So makes that. So we have this temperature, the first time x equals to 0, T0 equals to 40 degrees. Now after 2 meters we have the first node, the second node at 4 meters, the third node at 6 meters, and fourth node at 8 meters. And this will be the last one will be the fifth node, which is T at temperature at 10, distance 10, 200 degrees centigrade, total length is 10 meters. So assuming delta x equals to 2m, we can mark the interior points there, which we just had done. Now at node 1, Ti is equals to T1, Ti minus 1 is T0, and Ti plus 1 will be T2. And thus we will place these values in equation 2. This is the elliptic equation that we just developed. We will replace the values, and here comes the equation at node 1. With the little manipulation, we rearrange and we arrive to this equation of 2.04 T1 minus T2 equals to 40.8. We will carry on at node 2. So at node 2 now Ti becomes T2. You see a shift in I. Previously it was 1 here, it was 1 here, and now notice the Ti is now, because we are now talking about the second node. Similarly, Ti minus 1 now becomes T1, and Ti plus 1 will become T3. So on the similar way, we will rewrite the equation at node 2, and the equation is arranged like this. Similarly, at node 3, I equals to 3, we have this equation, and at node 4 we have the fourth equation, node 4. So thus we have 4. Before we proceed, I should mention this thing that T5 is the boundary value. T5 is the boundary value, this one. After T4, this is the T4. This one is T4, so this becomes T5, which is also the boundary condition. So T5 was known, is given as a boundary value 200. We replace this, and the equation becomes the fourth equation. Now thus we have 4 equations representing the temperature at the 4 nodes. So 4 equations, 4 variables. They can be written in here we write them together, and next we put them in the matrix form. Now this matrix form, it can be, we have the these can be figured out by using naive Gaussian elimination, or the best method will be the tri-diagonal method. Now we will start the partial differential equations. We just studied about the previous section was about the finite divided difference, but use to solve the partial differential equation boundary value problem. Now we will discuss about the finite difference methods which are being used for to solve the partial differential equations. Before proceeding, our focus will be the second order linear partial differential equations. So this is the general form for that one, where we have arranged the terms so that we have A, B, C, and D. Why we have done it? Because by using in this form we can calculate B square minus 4AC term, and that will help us to find if this is less than 0, so the partial differential equation will be called elliptic. If it is equals to 0, the partial differential equation will be parabolic, and if it is greater than 0, so the equation will be elliptic. And there are some examples. This is the Laplace equation we have, and this is the heat conduction equation, and this is the hyperbolic equation, for example. We will move to few examples. For example, this is we need to classify the partial differential equation given here. So it's better to rearrange them. We rearrange them, given equation. Here is the rearrangement. Equation 3 shows the rearrangement, and we can compare equation 3 with equation 2. This will give us the values for, this will help us to get the values for ABC. So these are the values here. So comparing this and give us A equals to 5, B equals to 0, and C equals to 6. Calculating the B square minus 4AC results in minus 120, which means that this equation is elliptic. We have another example, this one. Here also we rearrange them here in this form to compare, and after comparison we have A equals to 0, B equals to 0, and C equals to 5. Next we calculate B square minus 4AC, which results in 0, which means the equation is parabolic. The third one comes the elliptic example. This is the elliptic equation. We just rearrange them so that we have 1, 0, 5 for A, B, C respectively. We calculate the B square minus 4AC, which turns out to be 20, which is greater than 0. So this is hyperbolic. Next we will review the chapter 29, steady state partial differential equation. In this chapter, finite difference method is used to solve the elliptic partial differential equation. The example taken as to understand the method is the Laplace equation, where the temperature here is fixed. So Laplace equation, which is used to describe the steady state of a plate. So this is the Laplace equation, and in case if the temperature on the corner is not constant, this can be represented by the function like a source or a sink of heat, where the temperature may vary. So our target is to solve this partial differential equation. So for solving, it's easier to use central divided difference from figure 23.3. You can reference back to replace the differential of x by this formula, and with respect to the y by the correspondingly the other formula here. And just note down that the corresponding error is of order delta x squared. So when we replace the partial differential equation, this one will turn into this equation, and if delta x equals to delta y, the equation goes as follows. Delta x delta y cancels out. We will make some rearrangement here, and so we will have ti plus 1j, ti minus 1j, ti I plus 1, ti j minus 1 minus 4 ti j. Keep in mind that I plus 1 is used for x direction, while j is used for y. So this is called Laplacian difference equation, and the method holds for this equation holds for all interior points. And okay, so next we will switch directly to Lippmann's method. So Lippmann method uses the previous equation just we derived, this one, and we will rearrange this equation along with an improvement over relaxation operator equation. So by using this, ti j can be evaluated, and after we have this, we will put it here in the other equation 29.12 with the relaxation operator of lambda, which is here as a being factor, and its value should be between 1 and 2, so that we can calculate the updated value of Ij, the temperature. And the error can be figured out just like on similar grounds like we did for the Taylor method, that is the new value minus the old value divided by the new value for the approximated error. we will go through the example 29.1 quickly. Finding temperature of a heated plate with fixed boundary conditions. We are going to use the Lib method, and it's required that the over relaxation operator is 1.5, the weighing factor, sorry, and we need to iterate until we have this the error criteria, to match the error criteria of epsilon s equals to 1%, but we will do it for only few iterations, and because it's better to do it with computer. Now the solution, a redraw of figure 29.4 is here. Here we can see that the zero temperature on one side, 50 degrees, 100 degrees, and 75 degrees on the edges, and we have the interior points labeled I11, I21, I31, I12, 22, 32, 13, 23, 33. So the procedure should take, like, we will apply the equation 1 and equation 2 on every node, one after the other, and it goes like this. If we are talking about the first point ij, going towards right, it will be I plus 1 j, and to left it will be I minus 1 j, and if I go up it will be treated as I'm standing on the same point and moving in j plus 1, and if we move down it will be the same I, but j will be j minus 1. So at node 11 we have I equals to 1, j equals to 1, and the equation becomes t11, t21, t01, t12, t10, right, better 4. Sometimes you may notice that we write t1, 1, and sometimes we write v1, 1, so interchangeably we can utilize both of them to represent the temperature at node 11. Here the values are t120, t01, it's the temperature on the on this side. If t1 is this will be t01, and this will be your t1, 0. Alright, so and also keep in mind that we assume all interior points at the first time all at 0 degrees centigrade. So assume 0 degrees for all interior points for the first time, the starting point. So we substitute t1 to 0, t01 is 75, t10 is 0, t21 is 0. We substitute and we will have this value of 18.75. Once we have this value, we will go to apply the relaxation over relaxation operator as in equation 2 here, and using the lambda. So lambda is 1.5. We apply the equation 2, and now we are able to we get the value 28.12. So we will use 28.125 because it's not 18.75. This is updated value 28.25. Similarly, we will carry on for node 21. Relaxation operator is applied, and node 31, updated value, this one, this was in the previous one, and so on. Now I will switch to 29.2. Here we have the results from 29.1. Here are they. 29.5 figure is redrawn here with the temperatures. We can see inside like 43 here, and we can see 33 here, 33.89 here, and 63.21 here. And notice that the temperature at the edges are the same. And here we have to apply the we have to find the heat conduction, apply the heat conduction equation here to find the distribution of the heat flux in this plate. So this plate is 40 by 40 centimeter. Constants are given here. This is the equation from the Fourier's law, Qi, and just want to go quickly. And we have the first order differential here with respect to time, with respect to x, it's given by this. With respect to y, it's given like this. And so the heat flux will be calculated for both qx and y, x and y direction, and the resultant qn will be calculated by root qx squared plus qy squared, and theta equals to tan inverse of qy by qx. So at node 1 1 qx is calculated, and then we calculate qy here. I just want to be quick, it's quite straightforward. And similar notation is used. This is T11, T21 and T01, and if we go up, this is T12 and below is the T10 for node 1 1. That's why we are able to calculate qx, qy, and after we have qx, uy for the one node, we can go directly calculate qn, and from there further we can also calculate the theta. So the theta calculated is minus 56.58 degrees. So it means that the flux will be, let me draw it, heat flux here. This will be, if this is the point, it will be going down. It's minus 56. What was the value? Minus 56 degrees. Minus 56 degrees. Okay. Now, and we can continue with this. Now, review of the chapter 30. Here we will learn about the finite difference method, which will be used to solve for parabolic equation. Parabolic differential equation and parabolic differential equations are used to calculate the time varying problem. So in parabolic equation we will have a distance, one distance or two distance, and also the time. So time variable, this is the time variable problem, but the parabolic equation. So here is an example, assuming that we have one spatial variable, like let's say x distance, and then we have the time variable. So let's say on the y-axis we have the time. So we were using I for as an index for the x. Here we will use L as an index for moving in time. So previous time will be L minus 1, next time will be L plus 1. Let's see how it goes. So there is one addition to our variable ti. So this time it will have a superscript L here, which is used for time variable. And if we have two special variables along with time, so we will have ti comma j L. Next we have this is the heat conduction equation that we will use throughout the section in chapter to study the parabolic equation. And the methods that we have for solving the parabolic equation are explicit method, simple implicit method, and Crank-Nicolson method. This is also basically an implicit method. Coming back to explicit method, in explicit method to solve the equation, heat conduction equation, we just replace it. We just replace the square derivative and the simple first order derivative by their corresponding centered finite divided difference formulas, and we rearrange them. We can rearrange them, and finally we have the ti L plus 1 equals to ti L plus lambda ti plus 1 L minus 2 ti L plus ti minus 1 L. So notice that we are here, we will be able to find the temperature, and the next time we can estimate find the temperature at, for example, L plus 1 is the current time, so we will be able to find the temperature at current time by using the temperature at the previous time L. Okay, if T, if we assume current time index is L, in that L plus 1, so in that case on the right hand side we see all the values are in the previous time, so that's why it's also called explicit, and we can find this. So equation 30.5, this one, this is applicable to all interior nodes. The equation can be used to find temperature at each node for our future time L plus 1. Future time or current time, it's all about the current time, the time is there, and previous values we have them. Based on the present values at the node, we can it's only a matter of time steps that we're gonna use. So it will use at L plus 1 we need neighborhood points at the previous time. Now we will discuss the example 30.1. Express solution of the 1D heat conduction equation. Simple 1D heat conduction equation is being used here. So it's a 10 centimeter rod, and the temperatures at the points are given. We have T0 at 100 degrees, T10 at 50 degrees, and the constants are further given. Delta x equals to 2 and delta t equals to 0.1 seconds. By using the formulas, we calculate k here, k bar is here, and I don't want to discuss anything about the controlling. Okay, so finally we have the lambda here. Calculation is quite straightforward. I don't want to emphasize that right now. I would like to emphasize on the use of the equation. So 30.5, this equation we will go and utilize here. So we see here at the first time t equals to 0.1 second, at node 2 centimeters, I will be 1. So I is 1, and we are able to write so we are able to write t and I equals to 1 here. So we write here t11 equals to t10, L equals to 0 here, plus lambda t2 0 minus 2, t1 0 plus t0 2. So notice that L is 1 here, L is 0 here. We are able to calculate t11. Then we have so at 4 centimeter, 3 centimeter, 8 centimeter, and then this comes the second. This was t equals to, notice now this was at t equals to 0.1 second. Now the calculations, now we are going to calculate at t equals to 0.2 seconds. Now keep in mind that now L will be 1, so L plus 1 will become 2, right? And t1 2, and this for the first node. Here comes the second node, the third node, and this is the fourth node. And it's better to refer back to figure 30.4. It's not here, but you can go and see the textbook. Explicit method is simple, but but has some issue of stability, and the method excludes some of the neighboring points. For that, just go and see 30.6 on page 877. Therefore, implicit methods are designed in which overcome these problems, but they are a little complex. Next, we will go to implicit methods. A simple implicit method, and it's better to compare them. The implicit methods, they overcome the problems of the explicit method, that is the stability and excluding the information issue. So comparison, so we are going to compare explicit and implicit methods with respect to the points they use. Now consider the grid point for that is used for the explicit method. Here x indicate the grid point involved in the time difference, and the circle indicate the grid point involved in the space difference. So here we can see that the circles in the explicit methods, they are being they show that the spatial is the derivative differential with respect to x is using points at L time, while in implicit method we can observe that the circles which indicate the space difference, they are using the 3 points in L plus 1 the time. This makes it a little difficult because we are talking about the next time and they are unknown. While notice also that the time difference is same in both the crosses, if you see, which indicate the points used for the time difference, they are same in both cases. Okay, right. So in spatial explicit method, the derivative, that is derivative with respect to the x, is at time level L. Okay, we just saw this one. While here in the explicit method, the derivative is given by TL plus 1, Ti plus 1, L plus 1. It's better to just compare this one. You see, this is L plus 1, L plus 1, L plus 1, and compare this with the differential here. See, this is L explicit, L. So this is the main difference between them. Using 30.7 along with the 30.3, the previous equation, you see the time derivative, this one and this one are same. They are using the same formula, but the formula here is different for both methods. So the derivation here is the derivation of the simple implicit method. We substitute the derivatives correspondingly, and it goes after substitution. It's of these two. It's a matter of rearrangement, and here is the assumption of lambda. Next, rearrangement. So notice that all the temperatures at L plus 1 are unknown. Now this comes a little problem. All the temperatures at L plus 1 are unknown, so therefore we rearrange them into, so we will keep all the unknowns on the left side, and whatever is known we'll take it to the right side of the equation. So rearranging them, notice that all the L plus 1 terms are unknown here, so we will rearrange them here, and finally we arrive to this equation 30.8, where this is Ti minus 1 unknown, Ti plus 1, of course. Now for the first, this will also indicate the temperature. Ti minus 1 is also indicating the first temperature for this node, for the node 1. This equation is applicable to all interior points except the first and last. Of course, they are, because these 2 points are directly known to us, so we need to take them on the other side. So for node 1, that is T1, and node 4, that is T4. Next we here at node 1 I equals to 1, and the equation becomes like this. And so as we discussed that at this there will be a boundary condition, and this value can be represented like a function, running function, but it will be known, so we will bring it to the other side, and that's why this is brought here 30.10. Same thing happens with the last node, where this value will be known to us. This is the other side of the rod, and thus we will be able to replace it and take this value, take this form to the right hand side. It's basically the same equation, just a little manipulation. If we know something, we will take it to the right hand side. So application of implicit method will result in a set of m algebraic equations with m unknown temperatures. Note that there are m nodes, so for each node we will have one equation and one unknown. This needs to use system of algebraic equations like traditional system or Navier-Stokes elimination to solve the temperature at every step, and we can use it. So equation 30.1, it shows the simple implicit method to solve heat conduction equation. Here we have the example. This example shows the temperature profile, the distances at 2 centimeter, 4, 6, 8, 10. These are the boundary values. Constants are given, so we are able to use constants, and finally able to calculate lambda, which is used in equation. So next we start with equation 30.8. we write it for node 1, where I equals to 1, and time index is the first one, so L equals to 0. We write it down, and we notice that at this time the initial all interior points initial temperature will be 0. Okay, we can write it T10, T20, T30, T40 equals to 0. And also it applies to the boundary conditions, so boundary conditions will also be known to us. So substituting the values and solving, and it's quite simple, it's straightforward. So we will have first equation A1 at node 2, I equals to 2, and is still 0. Substituting in equation 30.8, resolving, and we will have this equation B1, we call it B1. The first one was A1, B1. At node 3 we will have the equation C1. The equation at node 4, I equals to 4, L equals to 0, and we get D1. So what we get is a system, a set of algebraic equations. Here are the equations. The first one, equation A1, we call it a B1, C1, D1, just to show that these 4 equations are evaluated at the first time. In the matrix form, we can write it down here, where T11, T21, T31, T41 are unknown. These are the temperatures at L plus 1. Now, once we solve them, so they will correspond to T equals to 0.2, and we will have, and by using from the book, we can directly, we just write it as a reference, that we will get these values when we solve this system of algebraic equations. Now let's solve for the next time. So for the next time, L will become 1 and T equals to 0.2. Node 1, equation 30.1. The first equation comes like this. Second equation, note down that here when we are starting, we will use the values of, for example, t11. So if the superscript is 1, for example here, okay, so it means that t21 we just calculated, t21 here, so 0.0406 will be used here. See, we can see this value is used here. So when we are going, all the previous values like t21, t11, t31, for example here, for example this one and this one, they will all take the values which were calculated in the first step, and thus we will arrive at we will calculate 4 equations. These are the equations in the matrix form, and you notice the unknowns are now at time at L plus 1, which is equals to 2 now. And by solving directly, we just for reference we put the values here after the solution of this. So a few points about the simple implicit method. The special difference approximation. This is the x distance. Okay, so the difference in the spatial differential approximation is ordered second order accurate, while the time derivative is first order accurate. An improved implicit method like the Crank-Nicolson method will be used to get the second order accuracy in both time and space. So Crank-Nicolson method, what it does, it uses the second order approximation for both. It uses the midpoint increment. Midpoint increment will be used in the time derivative to get the second order accuracy. So it goes like this. We use the midpoint of the time to calculate the time derivative improvement. So the second derivative in the space can be determined at the midpoint by averaging the difference approximation at the beginning of time and at the end of the time. We switch to, so the approximation is get by we include an averaging, a midpoint averaging for the spatial derivative. So we will have a new value for the derivative. We substitute in this equation, and the rearrangement will result in this equation. This example, we will directly use this formula using Crank-Nicolson method to solve the heat condition equation as before. At node 1, I equals to 1, L equals to 0. The equation goes like this. We notice that T01 is 100 here, T00 is 0, T20 is 0. Substitute back and we will have arrived to the first equation. Similarly, I at node 2, I equals to 0, the equation 30.14, substitute the values and we get the second equation. All interior nodes in 0 temperature the first time. At node 3, I0, the equation C1 here, and similarly for the fourth node. Thus the system of equation is like this. In matrix form we can write it like this, and which can be solved for T0. So the rest of the solutions will be similar. This ends the tutorial on the partial differential equations. Thank you.